Good morning. I'm Christopher Pope. I am the DevSecOps manager for corporate IT at ExxonMobil, and we'll be talking today about effective DevSecOps for containers. I've titled this Thinking Inside the Box. So I'll start with a quick disclaimer. The views I'm sharing don't necessarily represent those of my employer. They are my own. I've got a second disclaimer as well. I'll be talking about various security products, platforms, and solutions. Mentioning them does not constitute endorsement, and not mentioning your favorite tool does not constitute endorsement either. Please hold on to any questions about what's the perfect tool for your given situation, because as with much of cloud security and IT security, the answer is usually it depends. It depends on your budget, it depends on your scale, it depends on your risk appetite and the kind of risks that you and your organization are dealing with, and what are your compliance requirements. So there's a lot to think about when you're selecting a tool, but I'll talk about general principles that I think we can all find helpful. So I won't spend a lot of time on the introduction for containers. I think the majority of us here are familiar, at least at a high level, with application containers. We'll do a quick level set, and then we'll talk about some of the security aspects. And if you think Jordan looks nervous in this picture, wait till he talks about Kubernetes network policies. So containers definition, I kind of like the brief definition that Docker actually provides: lightweight, standalone, executable package of software. The goal of containers is to allow developers to package an application along with its dependencies, binaries, code libraries, underlying services, components, configurations into a single unit, with the goal of making that portable. So you can run that in different operating systems in different environments without getting into the challenge of it breaking or breaking other aspects of your tool set or your operating system. The goal with containers, of course, is to provide isolation so you can run potentially conflicting applications in different places on the same OS platform or easily move them to a different one. I like this image so much from Wikimedia Commons that I stole it with attribution. So this is just a quick contrast with application containers versus more traditional virtual machines. As you can see with the VMs on the right, they abstract the hardware. Application containers are designed to abstract the software. Virtual machines each have their own kernel, while containers running on the same host all share that host operating system's kernel. So let's talk a bit about history. Containers have been around a little more than a decade, and in that time, surveys indicate that upwards of 80%, likely upwards of 90% of organizations are using application containers in some form or fashion. A lot of the early uptake was in the developer test and just kind of promotion to production workflows, because developers could experiment with different configurations and not have to have a bevy of different operating systems running on different machines. It allows developers to collaborate, to share easily, and then when they're ready, to promote that image to production without the classic problem of, well, it worked on my machine. Containers, in addition, today in the last probably 4 or 5 years, uptake has increased in production so that by now the majority of enterprises and organizations are using them to some degree in production. Docker is the most widely used platform for building containers. You can do orchestration with Docker on a very small scale, maybe from smaller organizations using Docker Swarm. But for larger scale deployment and management of containers, particularly where you want scaling, high availability, and better monitoring, you need an orchestration platform that is more performant and higher scale than Docker. So Kubernetes is the platform of choice, which again is used by the majority of organizations. Docker and Kubernetes, I'll highlight, are, as many of you know, are not really direct competitors. They have some overlap, but they're really more complementary, and a lot of organizations are using both at some level. In the Kubernetes space, as we talked in some of our sessions yesterday, all the major cloud providers have managed Kubernetes services that are widely used. Not only Amazon, AWS, and Google, but also IBM and Red Hat. So let's talk about some of the security and functionality benefits that containers are intended to bring. Scalability allows you to spin up and tear down images to meet changing needs. So that's one that definitely helps from a performance standpoint. Containers allow you to have much greater consistency in your environment and reduce that configuration drift. So that helps reduce issues, but also from a security standpoint, you can have a lot more confidence with containers that key configurations aren't slowly being changed or modified over time. Containers are intended to allow fewer application conflicts, either with the operating system or with other things that are running on the same metal. Containers are intended to provide better utilization and more efficiency. One of the most common use cases is microservices. So a more monolithic application can be broken down into different layers that are each run on different container clusters. So this allows you to spin up and kind of rescale each of those layers as needed. From an efficiency standpoint, particularly for compiled code languages like Go, we can build extremely light, performant containers that contain really little more than the binaries needed. So this can allow us to get more out of our computing resources than if we were using virtual machines, for example. Containers allow fewer surprises when promoting code to development and production because of that consistency. And then from our perspective as security professionals, one of the big objectives of containers is to allow security isolation, not only from other things that might be running on that hardware, but from the host OS. And when containers are designed effectively, they allow you to reduce that attack surface and limit to a greater degree the ability for attackers to escalate privilege more broadly into the host operating system. So unfortunately, as containers proliferate, so do container security issues. In a survey last year, almost 60% of IT security professionals said they had experienced some kind of security issue related to containers. Some of the common factors cited included network configurations and issues with APIs, as well as problems with security certificates. 30% in some surveys indicated they had experienced a data breach or some kind of data loss as a result, which is very significant if that continues as a consistent number. Some of the consequences they cited in terms of business impacts included delayed product launches, disruption to services, and in a few cases, even violation of compliance norms that they were expected to uphold. More than 3/4 of container images in several studies have been found to contain at least one critical or high security vulnerability. Now, I know those of us in this room take that with a grain of salt. We're very familiar with the high signal to noise ratio that vulnerability scanners tend to produce. Very likely, only a small number of those vulnerabilities would have been exploitable at runtime. And I think if you read the fine print on some of those scary reports, you'll see an acknowledgement of that same fact. However, if our goal is still to try to shrink the top of that pyramid in terms of exploitable issues that present a genuine security threat, we've got to start by reducing the size of the bottom of the pyramid. And so if we're using the right practices to build and test containers, I think it's important to try to bring down that bottom number as well. So let's talk about containers as a two-edged sword. And I find this is helpful to think about the power of containers for good, as well as just like a two-edged sword, we can slice our fingers quite badly if we don't take care with what we're doing. We talked about scalability. Containers allow you to easily reproduce your preferred images across the environment and then update those when you're ready to add new security configurations or updates to the underlying application. That scalability also allows you to multiply or maintain outdated or insecure images throughout your environment. Containers are intended to provide isolation. In some cases, this helps maintain legacy code that's mission critical a bit longer with fewer issues related to operating systems being upgraded or other components constantly changing. Or containers can also be a vector for insecure or vulnerable apps to be allowed to exist forever without that push provided by operating system and other upgrades that can force application owners to, at some point, modernize their code. Containers can facilitate development and testing in unique and isolated environments. We talked about how valuable that is for developers to do that and then be able to promote those with fewer issues. Containers can also facilitate development of many unique and insecure environments that may not be directly visible to your standard enterprise security tooling. Portability. Containers allow easy sharing of images to speed productivity. Developers can collaborate, they can work with trusted third parties. The containers really make this easy without a lot of the headaches that developers traditionally face when doing that. Container portability also creates another vector for malicious code infiltration. People find container images on the internet, or they get container images from what they think is a trusted third party or a vendor that wants them to try something in the environment. Finally, the container ecosystem itself. Orchestration platforms like Kubernetes have very powerful control plane tools that allow you to manage and monitor your environment. Those same tools in the hands of someone internal that's inept or malicious, or in the hands of an attacker, can create massive disruption throughout your environment. I think as one author quipped, doing Kubernetes is not hard, but doing Kubernetes well can be quite challenging. Let's talk about a couple of additional security challenges. Several studies in the last couple of years have highlighted Docker registries exposed online with no authentication or limited authentication, including in few cases where literally anyone would have been able to stand up or destroy images in those registries. So again, to summarize, without the right security framework, containers can magnify and multiply security issues in your environment. We have the Bill Gates quote here: automation applied to an inefficient operation will only magnify that inefficiency. And we might say, in our context, automation applied to an insecure operation or process is only going to multiply the insecurity. So with that, I'd like to talk about a simple blueprint that enterprise IT security leaders should consider as a starting point for DevSecOps and holistic container security. I'll step through this briefly, and then we'll look at each of the steps in more detail. So the foundation is developer education, built on further by robust enterprise secrets management, securing the container registry, which is basically the nerve center where images are stored and distributed, container access management and making sure that you use robust role-based access for that, hardening container images to make sure that they're signed, trusted, secure, and updated, building testing for those images into our DevSecOps pipeline, and finally having a security assessment process and procedures that are cognizant of the unique risks presented by application containers. So let's talk about developer education a bit. And really, this is the essential foundation for DevSecOps for containers, in my view. It needs to go beyond just having developers know the basics of building what they want into a container and pulling out or stripping out the unnecessary components. We want them to have some kind of mindset about security. I think Casey mentioned in the keynote panel, we want to bake that security mindset into the build process, and container development is no exception. We don't necessarily want to just scare our developers, although that has its usefulness. And realistically, we don't want to convert them into security SMEs, although that would be great. What we really want is to cultivate this mindset of container lifecycle security and lifecycle management. We want developers not just to think about, how do I create a container image? How do I do that securely? But how do I make sure that image is maintained and sustained and ultimately pulled out of the environment when it's no longer needed? Secondly, secrets management for containers. This starts with not hard coding any secrets into container images. And developers, for one, need to understand that this is not just passwords, but anything that could be considered a secret, API keys, certificates, and all those things that really ought to be injected into the images when they're running and not baked in when they're created. We want secrets management for containers to integrate into our enterprise secret management solutions. And if you don't have an enterprise secret management solution, whether that's using Hashi or one of its many alternatives, that's probably another conversation you should be having. And you want to enforce that secret rotation via policy. A couple of container-specific aspects here. Looking at Kubernetes, specifically the etcd cluster, this is the cluster where secret and state information is stored, and basically, in effect, it provides root access to the whole cluster. If you're running your own Kubernetes, kind of self-managed in the cloud or on-prem, this cluster, every member of the cluster needs to have sufficient resources. In Kubernetes' own words, performance and stability of the etcd cluster is susceptible to network and disk resource starvation. So without the right resources, the etcd cluster can end up in a state where it's unstable, and that will stop you cold from rolling out any more pods until that's addressed. And in fact, in some limited circumstances, this can even be an out-of-memory attack vector, although I think role-based access, as we'll discuss, is the way to address that. Now, if you're using a managed Kubernetes service, this is one of the areas that putting your cluster management, or your cluster tool set in the hands of a service provider can help, but it's possible to still shoot yourself in the foot if you put resource limitations on this cluster that could affect what it needs in the case where it might be rapidly growing. Most of the major cloud providers with their managed Kubernetes service will send you alerts if they suspect any resource issues might be coming up for your etcd cluster, but it's up to you under shared responsibility to make sure you consume those alerts and you take action on those. One of the areas I want to highlight for Kubernetes is that even though Kubernetes itself and the managed services provided by cloud services have very respectable security capabilities, default configurations are not always your friend. In vanilla Kubernetes, if you're kind of doing that self-managed, the etcd cluster, which as I mentioned is kind of the administrative cluster with secrets for the cluster in it, is not encrypted by default. So that's something to be aware of. For cloud providers, Azure and Google do encrypt it by default, and there's also some various options that you can use to kind of manage that depending how you want those secrets to be managed and the keys to be managed. But for Amazon, as of today, it is not encrypted by default. They provide you with the capability, but that's something that you'll need to do yourself. And of course, you'll need a secure communication to the etcd cluster and restrict access to just the Kubernetes API services. It's hard to say too much about the importance of protecting your container registry. Again, this is kind of the nerve center where container images are stored and distributed. This could take the form of Docker Hub if you're using Docker, or this can be the Azure Container Registry, Amazon ECR, or if you're using Google, this is actually they use the Google Artifact Registry. So if you're using managed cloud services, you want to focus on standard principles here for strong identity and access management, network controls, and robust logging, and we'll talk more about that a bit later. If you're hosting your own Kubernetes in the cloud and manage that directly, you want to make sure that you harden and monitor not just the host where it's running, but also the storage that it uses. And I'll add here that you also need to ensure your container runtime is up to date, even if you're using a cloud managed Kubernetes service. And finally, you want to establish regular auditing processes, as we'll talk about in the top of the pyramid. So let's talk about container image security. There's 4 principles here that I'd like to highlight to build into your container images. Firstly, you want them to be trusted. And digital signing is kind of the industry standard way to do that. All of the major cloud providers integrate with Notary's notation product for digital signing. And that's also the solution that Docker Content Trust uses if you're using Docker Swarm. Secondly, container images need to be updated. And we talked about how this means rolling out the updated images and removing the old ones proactively and making sure that you're purging out any that are deemed insecure. You want to use a multi-stage build process to create very minimal images. Again, particularly for compiled code, this has a huge efficiency benefit. And it's also important in making sure that you're stripping out anything you don't need from those images. With a multi-stage build process, you're typically using multiple from statements in your Docker file and feeding the output of each into the next step. So for languages like Go, this can result in very, very minimal images that are very performant. Probably doesn't help as much if you're using compiled languages, but it's still important to have a build process that results in the smallest and most performant image possible. Thirdly, your container images need to be tested, and ideally that'll be done automatically as part of the build process, as we'll talk about shortly. You want to integrate that into your pipeline. There's a variety of products and solutions for testing container images. Aquasec Trivia is a popular one. Docker Bench is an open source option for those that are using Docker. And there's a number of broader cloud security products that also have image scanning capabilities. I'd mention Wiz, Orca, and Aikido. Kubescape is a more intelligent open source version, and one of the benefits of Kubescape is it only flags vulnerabilities that it sees being called in the code at runtime. So it can help to reduce that signal to noise ratio for lines of code that you may just not be executing. And finally, and fourthly, container images need to be hardened, which again means removing any unneeded services, build tools, or permissions that aren't actually needed at the runtime. Whenever feasible, if your application architecture allows it, you'll also want to make your container images immutable so that they are not able to run any code that might be injected when they're actually running. I'll mention here ChainGuard, which is a service that provides base images that your developers can then build on, and those images are intended to have 0 CVEs. So if that's important to you and your organization from a compliance perspective, you might want to take a look at ChainGuard. I'll mention that typically only the newest version of each image for ChainGuard is provided for free. If you want earlier versions, those can be quite expensive, so just be cognizant of that. So let's talk about access management for containers. And misconfiguration and excessive privilege for containers is one of the main issues that afflict container security. Needless to say, you don't want to run as root or super user. So you and your developers should be aware that if anyone passes them or gives you an image that requires root or sudo, whether that's from a vendor that wants you to do a quick POC on this product, whether that's from a container registry online, that's kind of an immediate red flag. A couple of other excessive privilege issues to be aware of. One is docker.socket. This should only be mounted if you have a container that's managing other containers, which is a pretty niche case. It's a pretty rare case. So other than that, you definitely don't want that in place. Another Docker-specific configuration to be aware of is allowing containers to communicate and connect with TCP socket. So it's something to be aware of there that can often be eliminated. In Kubernetes, you want to structure your role bindings to limit permission scope and use role bindings rather than cluster role bindings to limit that permission to a given namespace wherever possible. Avoid wildcard permissions, and definitely don't add users to system master for Kubernetes. Because if you do that, it basically circumvents all of the other role bindings and role revocations. I think it goes without saying in this group, but you want to implement robust multi-factor authentication for any human admin access and use very short-lived authentication tokens when providing access. So for network namespaces, this is an important Kubernetes feature that you should enable, and you want to limit pod networking as much as possible only to the necessary traffic. I talked about defaults not always being your friend in relation to Kubernetes, And in both Kubernetes and Docker, network communication between containers is often very permissive by default, probably more so than you really want in most cases. You also want to separate higher risk containers into dedicated clusters wherever possible. These could be containers that are dealing with more enterprise, mission critical, or revenue critical applications, maybe containers that deal with more sensitive data, deal with safety or health systems, or maybe ones that just relate to enterprise IT management systems that have a lot of risk. Definitely you want to separate those or use Kubernetes features like node affinity and pod anti-affinity to try to protect those from the risk of breakout from other less secure containers. But wherever possible, using dedicated clusters will add overhead for these, but it's definitely worth it from a risk standpoint. So let's talk about role-based access for Kubernetes. Note that overly permissive RBAC is number 3 on OWASP's list of container security risks. If you're using a cloud managed service for Kubernetes, you want to make use of their capabilities. I would strongly recommend you read Kubernetes RBAC good practices document just for an architectural foundation, even if you are working with a managed service, so you can understand some of those gotchas that I mentioned a partial list of earlier. Couple other items on RBAC. With respect to some of the pros and cons for the major CSPs, I point you to Dakota Riley's informative talk from yesterday. He delves into that in more detail, but from a general principles perspective, you strongly want to restrict any cluster admin roles. You want to limit list and watch permissions. It's widely understood that get permissions can allow users to view secrets, but list and watch can allow that in some cases as well. You want to limit users' ability to create persistent volumes because this can also allow them to read data from other containers. And you want to have frequent periodic review. You want to make sure that you understand what's going on and not just set and forget. For example, if an attacker could create an account with the same name as a deleted user in Kubernetes, unfortunately, they can inherit the permissions and rights that that user had. So let's talk about some other high-level security practices for a containers environment. If you're not using a managed Kubernetes service, you're running that yourself, you want to make sure that you harden your host operating system to reduce the risk of container breakout. This is one of the benefits of using a managed service, is that the cluster OS security is largely taken care of by the provider. You want to ensure you implement TLS everywhere if you're not doing that already, which hopefully those of us in this room, that shouldn't be a hard sell. And again, the default network configurations for containers are often your worst enemy. You want to make sure that you proactively address those. So let's talk about building a DevSecOps container pipeline. You want to track and manage images throughout the lifecycle with hash values. And you want to integrate those security testing tools into your pipeline and run those automatically as part of the build process. I mentioned Aquasec Trivy earlier as one that container security professionals often use. It's a bit of an oversimplification, but Claire, its functionality is kind of similar to an open source version of Trivy. Sneak is very popular as well because it integrates fairly seamlessly into the major managed Kubernetes services from cloud providers. Dockle helps you optimize the container image because it has some features to identify unnecessary privilege. It tries to look for hard-coded secrets and also any other issues like use of root or sudo. Anchor is another popular platform. In addition to image scanning, it also allows you to produce software bills of materials, SBOMs, for containers. And it does have a open source version, Gripe, for the scanning, and Sift for the SBOMs. Kyverno is a container policy engine that has some interesting capabilities, not only to set policies, but really to kind of throttle any containers that it detects in your environment that aren't compliant with those policies. And fortunately, it integrates well with all of the major cloud service providers, although it can be quite resource intensive to implement at scale, so be aware of that. And we've got a happy chain guard user there at the bottom. So finally, as we get to the top of the pyramid, let's talk about security evaluation practices. Again, set and forget is not the way to go. You want to continuously monitor container activity to look for anomalous patterns. Which tools you want to use for that, again, depends on kind of your administrative tool set and your architectural strategy. CubeShark is one that's popular. If you like Wireshark, it will be somewhat familiar. In fact, it was built by some of the original architects of Wireshark. Prisma Cloud from Palo Alto includes the functionality that older hands at container security might remember as twist lock and red lock, and it's pretty good for runtime scanning as well. And I think we've already talked about Dockle. And if you really are self-hosting Kubernetes and you feel very confident, Chaos Mesh is also a way to kind of introduce that chaos engineering mindset. So just to kind of conclude, assessing your container security health, no doubt you have procedures and guidelines for internal security assessments as well as for helping scope external audits. You want to make sure that you incorporate container-specific validations into those. And you want to scale based on enterprise and business risk. Again, focus on those container environments that have importance either to your revenue streams, to your sensitive data, or to the security of your IT environment. You want to communicate policies and consequences, unfortunately, for unauthorized containers, but try to use those as education opportunities to point your developers to hopefully the golden paths and the guidelines that you have that will allow them to do what they need in an approved fashion. So just to wrap up, to summarize, the foundation for holistic container DevSecOps is developer education, followed by integration with robust enterprise secrets management. Secondly, you want to leverage your container service platform capabilities to protect the registry and implement highly tailored restrictive role-based access. Thirdly, you want to secure your container images with digital signing, a structured build process, and build security test automation into your container pipeline. Fourthly and lastly, you want to monitor your container environment continuously, and you want to make sure that your security assessment processes include security assessments for containers that are scoped by risk. So with that, I want to thank you for your time, and I'm happy to take any questions.